Well, let's continue our thermodynamics lectures and start to talk about entropy in quite a bit more detail. So we talked a little bit about what entropy was. We talked about how it was really a measure of disorder, looking at energy, how many energy states are occupied versus how many are available. This whole idea of a disordered system having a greater amount of favor comes from a gentleman named Ludwig Boltzmann, and quite ahead of his time as far as how he perceived this idea of disorder. And he created this idea of microstates. And so a microstate is really a distribution of energy within a group of atoms. So if you were to look at, if we had like 4 particles and we had 2 packets of energy to distribute among them, we can see how there's 8 different ways to distribute those energies. There's 4 ways of distributing it with both packets of energy. I'm sorry, there's 10 ways. There's 4 ways of distributing the energies just on one atom, and 6 ways of distributing them on 2 different atoms. And so you can see how you're more likely to have the energy distributed among more atoms than it is on a single atom. So that gives you an idea of available states versus occupied states. So if we look at 2 vials that each have 2 particles, or a total of 4 particles. In a macrostate, you could say that you have 2 particles on each side. You would say that there's just one way of looking at that energy. However, in a microstate, you start looking at all the different positions. Maybe there's 4 different positions within each vial. And so the vial on the left could be 1 and 2, vial on the right could be 3 and 4, vial on the left could be 2 and 3, vial on the right could be 1 and 4, etc. You can see that if you have these microstates, there's just a lot more ways of distributing the energy, which was this whole idea of what Boltzmann was looking at. And so he eventually got to a very elegant mathematical representation of entropy, which we know as S, and this is just equal to K natural log of W. Now, it's a fairly simple equation as far as the number of variables it has, but it's actually fairly complex. It's not an equation that we really use at this level of chemistry. So we know that S is entropy. K is a constant known as the Boltzmann's constant. And if the funny thing with K is it's actually tied into the gas constant R. If you take the gas constant R of 8.314 and you divide it by Avogadro's number, you get this value here, Boltzmann constant, 1.381 times 10 to the minus 23. So pretty wild stuff there. So yeah, it's equal to R over NA. Now this W that we're taking the natural log of, so this is the number of equivalent microstates that are possible. So this is where you can imagine it would be very difficult to use this equation in a practical sense. However, it's very important in a theoretical sense. It's not something we are going to use in this class, but it's good just to be familiar with where this idea of entropy really comes from. But what this equation really implies is that the greater number of equivalent microstates that are possible, the greater the value of S is going to be. So what this means is that energy will distribute itself over as many atoms as possible in order to maximize the entropy of the system. Now, our second law of thermodynamics, we went through our first law a couple of sections ago. Second law of thermodynamics deals with entropy, and what it says is that the total entropy of a system and its surroundings, that's important, system and its surroundings, always increases for a spontaneous process. And one way of looking at the system and the surroundings, remember the system were the chemicals itself and the surroundings was everything else in the universe. So if you put those 2 things together, you have the entire universe. So what we're really looking at is the delta S of the system plus the delta S of the surroundings has to equal the delta S of the universe. And if the change in the delta S of the universe is greater than 0, well, then we are going to have a spontaneous process. And I think I mentioned this earlier, putting that burden of increasing the entropy of the universe onto just one single chemical reaction to occur seems like a heavy burden, but they always seem to manage because we certainly have a lot of spontaneous chemical reactions. Now, as you can imagine, it's a little bit difficult to measure the delta S. In the universe, we would have to measure the delta S everywhere in the universe. Really not something that is even possible for us to do. Now, for a given temperature, it's an easy matter to analyze the entropy for just the system. And we're going to find a way to work around this idea of delta S of the universe and to where everything gets based on the system and we'll take everything into account. So for a given temperature, we can analyze the entropy for the system using this equation. So we have delta S of the system is equal to Q reverse over T. Q reverse is the heat involved in a reversible process. Now, a reversible process is something that can go back and forth. So an example of that would be the melting of ice. So you can take ice in an ice cube, you can melt it into water, and then you can take that water and you can refreeze it. So the amount of heat involved in that is the same back and forth. So that is a reversible process. And the heat involved going either way is Q for that reversible process. So you take the Q for the reversible process, divide that by T, and that gives you the delta S of that system. Let's look at something just like this. So phase change. So here we want to calculate the delta S of vaporization. So we just have delta S vape. It just tells us what kind of process we have. So we want to change 1 mole of water, liquid water, to 1 mole of water gas or steam. So the heat involved in this process is 40.67 kilojoules per mole when we are at 100 degrees Celsius. We can have that process take place at other temperatures, so we always have to state what the temperature is. Otherwise, we don't have T for our equation. So we have 40.67 kilojoules per mole at 100 degrees Celsius. Now, when we are using this equation, we do have to make sure that we convert our temperature into Kelvin. If we were to use Celsius and we were at 0 Celsius, then all of a sudden we would have a dividing by 0 issue and we couldn't calculate a value for entropy. So we always use absolute temperatures for this kind of equation, and that way we don't have to worry about a 0 in the temperature because that would be absolute 0 and we can't reach that. So we are just going to have some positive value in there for delta S. So for our delta S for our Q reverse over T, we have 40.67 kilojoules per mole times 1 mole. We were told that we have 1 mole of water divided by the temperature, which is 373 Kelvin, and we get 0.109 kilojoules per Kelvin. Really weird units and kind of a tiny number. So generally what we see for entropy values is they're not in kilojoules. They use joules as their energy units per temperature. And so for this one, this would be 109 joules per Kelvin. Notice that my change in entropy is positive. We would expect that because we're going from a mole of water to mole of steam. We're going from liquid to a gas. That gives us a positive entropy change. We expect the system to become more disordered in going from a liquid to a gas, and this reflects that. A lot of that is caused by the fact that our delta H, or our Q involved for this, is also positive. We have to put energy into the system to go from water to steam. It takes energy to turn water into a gas, and so our energy there is positive. Our heat is positive, and that's going to give us a positive delta S. So all of these signs work in tandem with each other. You have to make sure that you keep them straight and don't ignore them. So once again, delta S positive, which is what we would expect, represents an energy change for the system only. This has no bearing on the surroundings yet. We are going to find out how to do the surroundings soon, but for right now, the only thing we've done is calculate the entropy change for the system. Okay, we saw it was a positive entropy change, but we know that that system is not spontaneous, just turning water liquid into water gas or steam, because otherwise our water would be boiling all over the place. It doesn't do that. So that was for the system only. Now, again, we're going to focus on surroundings a little bit later. Now, when we are looking at entropy of an individual substance as opposed to a process, we can determine the entropy for that substance under a set of given conditions. And so once again, we are going to use our idea of standard conditions, but we are also going to have to set some baseline for our value of entropy. What is ordered? What is perfectly ordered? What is disordered? So the third law of thermodynamics states that a perfect crystalline material at exactly 0 Kelvin will have an entropy equal to 0. So this is a kind of a philosophical, a theoretical baseline, because we have that 0 Kelvin there, and that will give us a entropy of 0. So perfectly crystalline material. What that means is that every atom is exactly where it's supposed to be. It's not vibrating back and forth at all. It has 0 thermal energy and nothing is moving. Now, as soon as the temperature goes higher than 0 K, everything will have a positive entropy. There's no such thing as negative entropy. You can have negative entropy change, but you cannot have a negative entropy. Make sure you know how to distinguish between those two. So as soon as we go into positive temperatures in Kelvin, that's the only way you can go, you will have a positive entropy because you start to have some thermal motion in there. So when we raise the temperature, we increase the entropy of our system. If you go to a phase change, to a more disordered phase, in other words, solid to liquid, liquid to gas, you're going to increase the entropy value as well. And then if you have a molecule that becomes more complex, the higher the entropy value would be. And that's a very important point there, because it means that you can actually have liquids that have a higher entropy than some gases. If you have a very simple gas, something like H2, it can actually have a lower entropy than a liquid if that liquid has a very complex makeup. So because that more complex molecule adds a lot of entropy in its possible disorderedness. So I mentioned earlier that we do use standard values for entropy. So we use the same set of standard conditions that we do with enthalpy. 298 Kelvin, 1 atmosphere or bar of pressure. Solutions are at 1 molar. And so because we now have a standard set of conditions, we can take our values of entropy for our different substances and tabulate those. And here's just some examples of what you might pull out of a table. This is out of a different book, so pay no attention to the number on the table. But here we see our joules per mole Kelvin. We calculated just joules per Kelvin earlier because we already knew how many moles we had. If you don't know how much material you have, then you have joules per mole Kelvin. And again, that the mole and the Kelvin are underneath the divisor sign there. So we see here as the molecules become more complex, even in the gas phase, they become a little more disordered, have a higher entropy. But look at this. Here we have methanol liquid has an entropy very close to this gas here, H2 gas. Br2, bromine liquid. Bromine is a very large atom. You put 2 atoms together, that's a pretty large system with lots of electrons, which means you have lots of possible energies that can really be dispersed over a lot of different particles. So we have a pretty high entropy here, 152.2. It's higher than the entropy of gas, or of this H2 gas. Same thing with benzene, also a fairly sizable molecule here. It's got 6 carbons, 6 hydrogens, and there's lots of different things that can happen. So it actually has a higher entropy in a liquid form than even argon or hydrogen have in a gas form. And even down here we have a solid at 142.3, FeCl3, iron trichloride, or iron 3 chloride. Lots of electrons involved in there, so lots of different microstates, and we have a fairly high entropy at 142.3. So here we have a solid with a higher entropy than this gas up here. So it really depends. We can't just use the phase to determine higher or lower entropies. You can make some guesses, but then you should always back it up with some calculation there. Now, when we are doing our entropy changes, we can calculate entropy changes for both physical and chemical processes using an equation very similar to what we used for enthalpy. And this is because entropy is a state function. So we can calculate that entropy change just by looking at what is the entropy of the products minus the entropy of the reactants. And the little n's that we see here just remind us that we have to use our stoichiometric coefficients just like we did with enthalpy. So we have delta S is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. So here's an example. We want to know what is the entropy change of this reaction here. So the burning of ethanol, we have C2H5OH plus 3O2 goes to 2CO2 plus 3H2O. We have all of our values here. So we have products minus reactants. So we have our 2CO2 right here, our 3H2O right there. We've got our 1 ethanol right there and our 3 O2s there. Notice that for something in its elemental state, oxygen does not have a zero entropy like it does the enthalpy. You have to be very careful of that. You should never have a zero value for entropy. Okay, everything has an entropy, everything has disorder in it. Okay, so products minus reactants there. Again, be careful when you're looking up some of those values. We've got that the water in a gas form, so you've got to be careful about that because you will be able to see water in liquid or water in solid form in that table. You want to make sure that you're looking up the correct value. Ethanol as well. Ethanol is generally present as a liquid at room temperature. This particular reaction uses it as a gas, and that's okay, but they're going to have different entropy values, so you always want to make sure you're looking up the correct one. And so when you work out this problem, you get an entropy change of 96.09 joules per Kelvin. And so we see that positive entropy change, and a couple things might make us guess that. We're going from 4 moles of gas in the reactants to a total of 5 moles of gas in the product. And so that gives us a little bit of entropy boost as well. So we're going to expand this idea of entropy just a little bit here, and then we're going to continue this discussion in the next set of slides. And so we learned earlier that the change in entropy of the universe is equal to the delta S of the system plus the delta S of the surroundings. Now, we've seen how to calculate the delta S of the system. We just need to know how to calculate the delta S of the surroundings. Well, we know that delta S of the system is equal to Q reverse over T. Okay. The other thing that we know is that Q reverse is equal to the delta H of the system. Remember? So the amount of heat involved in a reversible process is going to be equal to our enthalpy. And so we also know that the delta H of the surroundings is going to be equal to the opposite of the delta H of the system. Okay, this has to do with the flow of heat. So if the system is producing heat, losing heat, then the surroundings would be gaining heat, and vice versa. If the system is gaining heat, then the surroundings must be losing heat. But it's the exact same amount of heat. So the delta H of the surroundings is equal to the opposite of the delta H of the system. So if delta S of the system is equal to Q reverse over T, then the delta S of the surroundings must be equal to negative delta H of system over T. So negative delta H of the system would be equal to Q reverse of the surroundings. And so that would give us the delta S of the surroundings. So we can use the delta H in place of that Q reverse. And so now what we end up with here is delta S of the universe is equal to negative delta H of the system over T plus the delta S of the system. So now we are able to calculate the delta S of the universe, the change in the delta S of the universe, using only values that we obtain from the system. And that's really important because now we don't have to worry about the surroundings, because the surroundings are just too daunting. Once we got everything focused down to the system, now we can actually do some calculations. And we're going to explore that in the next set of slides.